Hi, this is the CS398 bit counting algorithm explanation video. So in this video, we're going to be dealing with 8-bit numbers. In the Lab 2, you're going to be dealing with 32-bit numbers. And in this example tutorial, I'm going to be using this 8-bit number, 01001101. And in this 8-bit number, we have 4 1-bits, 4 1-bits that we want to count. So the way we can actually do this is we can separate each of these bits into its own little number, and these are theoretical numbers. We're not actually going to put these bits in code, but this is how the algorithm works. So when we separate these the 8 bits into 1-bit numbers, instead of having to add all those together separately, what we can do is we can add them in batches. So we're going to separate the numbers to create 2-bit numbers. So basically, we know that if we add 1 with 1, if we don't have a 2-bit number, it's going to overflow. Show you that right now. 1 plus 1 is equal to 0 with an overflow of 1. So to actually add 1 with 1, we actually need a 2-bit number, so we can get 1, 0. And so likewise, we want to separate these 8 bits into basically 8 2-bit numbers. 8 2-bit numbers, which is the same thing as saying 2 8-bit numbers with the same number of bits. So 8 times 2 is 16, 2 times 8 is also 16. And we do this using the masks, which the handout calls even masks and odd masks. And so the even mask would be this, and the odd mask would be this. Now notice how when we do the odd mask, it's the same as appending 0, 1 next to each other a bunch of times. And with the even mask, it's actually 1, 0 appending next to each other a bunch of times. And this is not in the same alignment because 1, 0 has the least significant bit on the left side. So this is the LSB. This is the most significant bit. Whereas with the odd mask, we have the LSB here, the MSB here. So if we were to split these numbers actually into 2-bit numbers, it would look kind of like this. And then here, it's actually split up like this. So the way to get these green lines to align with each other is to right shift the even number by 1. So let me quickly give you the calculations if you were to apply these masks to the original number. So here's where the even one will go, and here's where the odd one will go. And so the result of the even one is 0, 0, 0, 0, 1, 0, 0, 0. And the one with the odd mask will be 0, 1, 0, 0, 0, 1, 0, 1. Notice how we still have 4 1-bits, which is what we want to end up with in the final answer. Okay, so now we need to, like I said, we need to right shift this even one by 1. And after we do that, we get 0, 0, 0, 0, 0, 1, 0, 0. And for the odd one, we're just going to keep it the same. 0, 1, 0, 0, 0, 1, 0, 1. And so now we have our 2-bit numbers aligned, and we can add them together. And so that's 0, 1. This is going to be 0 carry the 1, 0, 0, 1, 0. And here's where the magic actually happens. So we basically just lost a 1 in the bit, but if we actually consider these as 2-bit numbers, which what I've been saying all along is this is 1, this is 0, this is 2, this is 1, sorry, this is 1, and we add them together. Notice how we still get 4. Okay, so what just happened? So the whole trick behind this is we can use an 8-bit number to represent multiple smaller bit numbers. And so here we have one 8-bit number represent 4 2-bit numbers, right? And here we also have another 4 2-bit numbers. So actually we're adding together 16 2-bit numbers. Oh, sorry, 8 2-bit numbers, like right here. We're adding 8 2-bit numbers at the same time in parallel. And we're going to get 4 2-bit numbers as a result. And we can continue to do this with more masks. So on the next step, so now we have this 8-bit number consisting of 4 2-bit numbers, like I have down here. And we're going to mask them with new, even, and odd masks. So the even is going to be in blue, the odd is going to be in red. And so like before, instead of selecting 1-bit numbers, since now we have 2-bit numbers, we're going to use a different mask. So this is 1 1 0 0 1 1. Did I just lose a bit somewhere? Oh, I didn't. Oh, yes, I did. Sorry, 1 second. Okay. 0 0 1 1 0 0. Okay. And now for the odd mask, it's going to be 0 0 1 1 0 0 1. So notice how these masks are different than the mask we used the first time, because now we're selecting 2-bit numbers instead of 1-bit numbers. And so we're going to create 4. Yeah, so we're going to create 4 4-bit numbers and add them together. Okay, so when I mask the this black number with the blue mask, we're going to get 0 1 0 0 1 0 0 0. And when I mask it with the red mask, I'm going to get 0 0 0 0 0 0 1. Lost another 0 there somewhere. Right there. Okay. So this is the evens, and this is the odds. And just like before, I need to right shift the even numbers, but this time, because they're 2-bit numbers, I need to shift it by 2 instead of 1. And so after I shift it by 2, enough space. So after I shift it by 2, I'm gonna get 0 0 0 1 0 0 1 0. So I'm just gonna copy the odd number back down here, 0 0 0 0 0 0 0 1, and I'm gonna add these two together. So let me just do that real quick. 1 1 0 0 1 0 0 0. Now, like I said before, this time we have 4 4-bit numbers. If I draw the line right down the middle, we have this 4-bit number, which represents 2. This 4-bit number, which represents 1. This is 0, and this is 1. So when you add these 4 together, we still get 4. Now, when we have the answer, like down here, we have 1 and we have 3. So 1 plus 3 is 4. So these two are the exact same thing. And actually, we don't have to do anything else because we can just max these two numbers by having 0 0 1 0 0 0 1 0 0 1 1. And we can mask that with 1 1 1 1 0 0 0 0 to get this left side, and we can mask it with 0, 0, 0, 0, 1, 1, 1, 1 to get this side. And don't forget that you need to right shift this answer by 4 to align the bits. And so at the end, you should get 0, 0, 0, 1 plus 0, 0, 1, 1, which add together would be the binary representation of 4 in base 10. And that's how you bit count using this algorithm. I hope I was able to make a little bit more sense of the algorithm. If not, it's understandable because it's pretty difficult. Okay, thanks.